Hi everyone. It's my great pleasure to give a talk in IJTCS to talk about my recent work in peer prediction. And this work has been published in this year's SODA. Okay. Okay. So let me first ask you 3 questions. Do you like McDonald's? Do you like Subway? And do you like KFC? And so I want to incentivize you to tell the truth about these 3 questions. So one thing I can do is I can design proper reward systems to provide you some money to incentivize you to tell the truth. But the problem is the answer you provide is actually subjective. There is no way I can verify your answers. In this case, I cannot use some traditional method like spot checking. I check your answer with some probability and give you $1 if you can pass my check. Another way we can do is maybe we can do this agreement-based reward. So maybe if I will pay you and your friend based on the number of agreements you have. But still, it's going to discourage minority, and moreover, it's going to encourage uninformative feedbacks. Because if I only pay you according to the agreements, if you are the minority, you will lie. And also, like, you can collaborate with your friends and to give all restaurants the highest review. In such case, you actually provide no information, but both of you can get the highest amount of payment. And this work actually proposes a novel reward system that is, first, it achieves almost the best game theory property. It is stretch proof. So basically, it just means that regardless what other people are gonna see, tell the truth gonna pay you at least is the highest, and also is actually pay you strictly higher than any other strategy that is actually has less information than truth telling. And I will tell you the formal definition about this less information mean. And another thing about this reward system is that it is prior independent. So basically, the implementation of this mechanism actually doesn't need any prior knowledge. So you doesn't need to know anything about the restaurants or anything about the participants who answer your survey. And the third thing is this reward system is practical. Each participant, they only need to answer 2 times C questions. And C here is the number of choices. And for example, if in the fast food restaurant case, if I ask you, do you like it or not? So it is actually a binary choice question. And in such case, this reward system only requires each participant to answer 4 questions. And why I highlight this property here, because actually the previous work, they can achieve prior independent and they can be strategy proof, but they actually need to require each participant to answer an infinite number of questions. And this is the first practical strategy proof reward system. Okay. And also, this work also proposes a novel scoring rule that identifies high-quality information without the full knowledge of ground truth. And okay, so before we talk about the solution, let's first introduce the model and assumptions. So I still use the running example I mentioned before. So we have several fast food restaurants here, and we want to elicit people's reviews about these restaurants. And for simplicity, I just use binary case as an example, but actually the mechanism actually works for non-binary case. Okay, so in the binary case, we assume we have 2 participants, Alice and Bob here. So they're gonna provide their reviews for this fast food restaurant, like it or dislike it. And the problem is we need to design a reward system that takes the participants' reviews as inputs and then outputs a reward for each of them. Okay. And here is notations. So we have T restaurants with the review space C. In the binary case, C just, you can think the size of C is 2 and C equals 0, 1 or like or dislike. And for Alice, her honest reviews, we use XA1, XA2 until XAT to denote because the T here, because we have T restaurants. And actually, her honest reviews are unknown knowledge for us. There is no way for us to access this knowledge. The thing the mechanism can access is Alice reports, which we put the head here. And we have similar definition for Bob as well. So I still want to emphasize here, we only have access to XA head and XB head. And also, that is why we call it peer prediction, because the reward function, so the reward Alice and Bob, they're gonna get only depends on their reports, XA hat T and XB hat T. So there is no other side information. Okay, and after I talk about the setting of the mechanism, so let's talk about the strategy model. So here we assume for each task, Alice strategy can be seen as a confusion matrix. So you can just like, don't read the lines there. You can just like read the picture here. So here we have like 2 times 2 by 2 matrix. So basically it means that conditioning on Alice doesn't like this restaurant with 0.8 probability, she says she doesn't like, she tells the truth. And with 0.2 probability, she lies. And the second row means that conditioning on she likes the restaurant with 0.9 probability, she tells the truth. And with 0.1 probability, she lies. And this is actually a translation matrix, and it represents Alice's strategy for one task. Okay. And actually, we're going to call the profile of Alice and Bob's strategy profile. Okay. And here are several examples of the strategy. So maybe let's go back to this example again. So here, actually, when Alice performs this strategy, she actually doesn't tell the truth. And if she tells the truth, basically, conditioning on she doesn't like the restaurant, she's gonna say she doesn't like. And conditioning on she likes the restaurant, she's gonna say she like. And in this case, this matrix becomes the identity matrix. And if she always permutes her answer, when she likes the restaurant, she says she doesn't like, and when she doesn't like, she says she like it. In this case, the matrix becomes the permutation matrix. And that is the first row of this slide. Represents the truth-telling strategy and permutation strategy. And the second row here, I call the first one, the left one, I call it random guessing. So basically, it means that regardless of her own opinion, she always say she doesn't like the restaurant with 0.7 probability, and she likes the restaurant with 0.3 probability. So that is the random guessing strategy. So in such case, Alice actually ignores her own true opinions and always perform the same random samples in here. And the right one is always C1. So basically, regardless of her own opinion, she gonna give all restaurants, like she gonna say she likes all the restaurants. Okay, and for the third one, third row, I call it mixed strategy. So actually, the second row is also mixed strategy. The third one is special here because we can see that although Alice doesn't tell the truth, and Alex like sample her actions like based on her true opinion, but the first row is actually different from the second row here. Unlike the first row of the matrix is different from the second row of the matrix, which is unlike the strategies of the second row, the random guessing and always C1 strategy. Okay. So why I list 3 different kinds of strategy here? Because I want to see that the first one, like Alice tells the truth or Alice premieres her answer, both of them are fully informative. Maybe you're gonna see like if Alice performs the permutation strategy, she always lies. But from an information theoretical view, it actually has all the information you want. You just need to find the right way to interpret the information. So from this view, both truth-telling and permutation strategy are fully informative. And the random guessing and always say when, in such case, Alice always ignores her true opinions. And this kind of strategy, we call it uninformative strategy. Because if Alice performs this kind of strategy, there is no information contained in her feedback. And for this mixed strategy thing, it is actually partially informative. Because even though like Alice doesn't perform the fully informative strategy here, because she actually does different thing conditioning on her true opinion. So it is still a leak part of the information here. Okay. So after we talk about the strategy model, let's introduce the three assumptions we make in this work. The first one is a priori similar. So it just means that all tasks are very similar, so they have the same prior. And if you're familiar with machine learning, you can understand this assumption. It just means that Alice and Bob's true opinions, XAT and XBT, are IID samples. And we are not only want their true opinions, IID samples. Remember that we can only have access to their reported reviews, which will not be their honest reviews. And in this case, we actually assume that they play the same strategy for all tasks. And here I mean same, it doesn't mean they always need to perform the pure strategy. They can perform mixed strategy and use actually the randomness independent for all tasks. And basically, they just need to play the same strategy for all tasks, and strategy can be mixed strategy. And with this assumption, one thing we can get is that not only their honest reviews are IID samples, their reported reviews are IID samples as well, and that is actually very important for our mechanism. And the third one is, so remember the key insight of peer prediction is we reward the participants based on their peers' reviews. And in this case, we need to assume that these participants' reviews are correlated in some way. So in this simple two participants case, we just need to assume that their honest reviews are strictly correlated. And basically, they cannot be independent of each other. And here I give you a formal definition for strict correlation. So it just means that if we use U to represent the joint distribution matrix over Alice and Bob's honest reviews for a random task, the random variable denoted as XA and XB. And in such case, we assume that this joint distribution matrix actually has non-zero determinant. So let's just see the following two examples here. So in the right one, it just means that with 0.25 probability, both Alice and Bob doesn't like the restaurant. And with 0.25 probability, Alice likes the restaurant and Bob doesn't like the restaurant, and it's same thing for others. And the left one means that with 0.3 probability, both of them dislike the restaurant, and with 0.25 probability, one like, one dislike, and with 0.2 probability, they both like the restaurant. And we can see that in this case, these two joint distribution matrix, the right one actually has zero determinant and doesn't satisfy our strict correlation assumption. And the left one actually satisfies it. Okay. Okay, fine. So after we discuss the assumptions we need for this work, finally, let's talk about what is the mechanism design goal? What kind of reward system we want to design? So we want to design reward system such that the truth telling is the dominant strategy, and actually strictly dominant other less informative strategy. So what does less informative mean? So remember the three roles I showed you before. So the permutation strategy actually contains the same amount of information as truth telling. So that one is actually equivalently informative as truth telling. So there is impossibility results showing that if the mechanism is prior independent, it doesn't know any prior information about the participants and the restaurants, it's impossible to design a mechanism such that truth telling is strictly better than any other strategy. I mean, like the permutation strategy. And in this case, we doesn't need the truth telling being strictly better than the permutation strategy because they have the same amount of information. We just want truth telling is the best and strictly better than the uninformative and partially informative strategy. And also I introduced an approximate version of this mechanism design goal here. It calls epsilon delta dominant truthfulness. So it just means that with high probability, 1 minus delta, and truth telling is greater than other strategy minus epsilon. So I want to emphasize here why I introduced this one. It doesn't mean that the mechanism in this work is the approximate version. So the mechanism in this work actually can be perfectly strategy proof. The reason I introduced this definition because the previous work, some of them only achieve the approximate version of this strategy proof goal. Okay. Okay, so let's talk about the previous works. So in 2004, Miller, Resnick, and the others, they started the literature of peer prediction. So the first work, similar work of peer prediction, they actually want to solve this, do you like this restaurant or not? This kind of question. But in their work, they only consider the settings that each participant is only as a single question. And basically they only need to review a single restaurant. And in this case, although this setting actually can be considered has less information than the setting this work, like the several fast food restaurant, like the setting we discussed before, but actually in the single restaurant case, the mechanism is first, it's definitely impossible to design a strategy-proof mechanism, and also it has many restrictions. For example, in their work, they need to know the prior knowledge over the participants. And in 2013, the Scoop and Ghosh, they actually start this multitask peer prediction setting. So it's like several fast food restaurant case. And actually they propose the first multitask peer prediction mechanism where truth telling is a strict equilibrium. So it means that if other people tell the truth, even you're the minority, your best strategy is tell the truth as well. And also they can prove that the truth telling is the best equilibrium. However, there are still several restrictions in their work. First, they can only work for binary choice questions. And second, they only work for positively correlated participants. So you can understand is like the participants, they need to have similar tastes for the restaurants. And third, the most important is not strategy proof. Okay. And after that, these three works actually resolve some of the limitation of that one. So they all work for non-binary case. They can achieve the strategy proof property, and they do not need to assume some prior knowledge over the participants. But still, let's see, if they want to achieve the perfectly stretch-proof property, they all need the participant to answer infinite number of questions. And they can ask the participant to answer only a finite number of questions, but this version of mechanism can only achieve the approximate version of stretch proof. And let's see why this previous mechanism, they need an infinite number. So basically, intuitively, they actually need the infinite number of tasks to learn the information structure over the participants. So basically, they want to know whether the participants have similar tastes, and in such case, they should be rewarded for agreements, or they actually have opposite tastes. In such case, they need to be rewarded for disagreements, or they actually have very complicated information structure. And in this case, they should be rewarded for complicated agreements. And we can see that because of that, because they actually all follows from that kind of paradigm. So that is why no previous strategy proof mechanism works for a finite number of tasks. And this work proposes the first one, which actually can be strategy proof and works for finite. Actually, not only finite, it's actually a very small constant I mentioned before. It's just 2 times c. And in the binary case, even the previous work requires infinite number, and this work only requires 4. Okay, so finally, after the long setup, the models, the assumption, and the previous work, let's see the solution. So the idea is to actually still follow from my previous work, the information theoretic framework to design a peer prediction mechanism. So basically, we want the expected payment of the participant, in the 2 participants, Alice and Bob. We want each of them, the expected payment equal the mutual information between their answers, and such that this mutual information is information monotone. So basically, it means that if Alice performs some strategy as A there, and it's gonna decrease the amount of information contained in the feedback. So it's gonna decrease the mutual information between her feedback and Bob's. And maybe people are gonna ask, here is it seems like Bob needs to tell the truth here, because I don't put any head signal here. But actually here, the Bob here can be replaced by non-truthful Bob. It doesn't matter. This information monotonicity inequality is going to be true. And the second one is also the most important one, because if you are familiar with information theory, you're going to see, okay, that is just data processing inequality, and the traditional Shannon mutual information satisfies that. And why you just choose Shannon mutual information? It's just because the second one, we not only want this mutual information being an information monotone, we also want that we can construct an unbiased estimator with a smaller number of tasks. And there are several candidates. We pay the agents according to, we pay the participants according to the number of agreements they have. And in such case, it is not information monotone, because if Alice knows she is a minority, and in such case, if she lies, it's gonna give her strictly higher payment. So that is not information monotone. And the second one I mentioned before, the Shannon mutual information, it is information monotone, but it cannot be constructed. Its unbiased estimator cannot be constructed only via a small number of samples because of the log thing. And in this case, to apply this idea in this multitask peer population, one biggest challenge is we need a new definition of mutual information. And the idea of this mutual information is actually quite intuitive if you just see this slide. So we can see that the first one is fully informative, the second one is uninformative, and the third one is partially informative. If you read this slide over 3 seconds, you may notify that a more informative strategy has a higher determinant. So the first one, the determinant, has a higher absolute value of the determinant because it can be positive or negative. So the first one has the highest one, 1. And the second one is 0. And the third one is actually between 0 and 1. And that comes to our new definition of mutual information, the determinant-based mutual information, DMI. So for 2 random variables, x and y, which have the same support C, we use U to represent the joint distribution, and the determinant-based mutual information is just defined as the determinant of this joint distribution matrix. You just add a absolute value there. And when we can easily prove with the matrixing, because it we know that the determinant A, B equals determinant A times determinant B. Actually, I'm going to introduce you the details later. So basically, we can easily prove this definition is information monotone. And the most important thing is that if you just square the DMI, you can obtain a polynomial of the joint distribution matrix entries. And actually, it's very easy to construct an unbiased estimator if it's just a polynomial, because you only need the number. If the degree is d, you only need d samples to construct the unbiased estimator of it. And that is the key trick of this work. Okay, so finally, we see the solution. It's like this. So we have 2 participants, Alice and Bob. And in this example, they are assigned 11 restaurants here, and they provide their reviews. So the red one means they don't like the restaurant, and the green one means they like the restaurant. And one thing that's important is we actually assign this restaurant to them in a random order. So we want to avoid the case that they close in advance and saying that, okay, the first restaurant we both don't like, the second one we like, and the third one we like, something like that. So we're gonna assign these restaurants to them in a random order, and moreover, they actually, when they answer the questions, they cannot communicate with each other. So that's one thing I want to mention here. And then after the mechanism collects their feedbacks, their opinions for these 11 restaurants, and then we're gonna divide these 11 restaurants into 2 batches arbitrarily, as long as each of them has numbers greater than C. So here in the binary choice thing, C equals 2, so we only need each group has at least 2 restaurants. And then for each group, we're gonna get this counting matrix here. It just counts within this group, how many restaurants they both don't like. So in the upper one, it's 1. And how many restaurants one like, one dislike. And depends on if I forget which one is maybe the one Alice like and Bob doesn't like is 2, and the one Alice doesn't like and Bob likes. None of the restaurant in the first group they both like. So in such case, we obtain this 2 by 2 counting matrix with these integers. And similarly, we obtain the one for the lower group. And we're going to pay them the product of the determinants of these 2 matrices. And it's actually pretty easy to describe the mechanism. And we're going to show that this mechanism is the mechanism we want when the total number of the restaurants greater than 2C, such that we can actually get these two groups and each of them has size greater than C. This mechanism is dominantly truthful, i.e. strategy proof, and prior independent. So we can see the implementation of this mechanism doesn't involve any prior knowledge about restaurants or about the participants. And more importantly, it works for at least 2 times C tasks and at least 2 participants. Because if like the 2 participants case work here, in the multiple participants here, you can just like do whatever you like. For each one, you can randomly pick as one as her peer, or arbitrarily pick one as her peer, or just average the average choosing. But anyhow, if you can solve the 2 keys, you can solve the general case easily. For this number of participants. When I give this talk, like many people ask the question, why you have this limitation? The lower bound, it should be greater than 2C. It's just because that we need this because we want the determinant of this 2 counting matrix being non-zero. So even though it can still be 0 sometimes, but we want in expectation its determinant is not 0. And if you only have, for example, if like C equals 2 here, and if you only have 1 restaurant here, and in this counting matrix, you need to put this 1 in like one of the entry. And in such case, no matter what you're gonna do, the determinant of this matrix is gonna be 0 forever. And that is why we have this lower bound 2C. Okay, so now let's start to prove the math theorem. First one is it is information monotone, and the second one is we need to prove that the expected payment is the square of the DMI between Alice report and Bob's report. So the square is in like some other, oh, sorry, I forget to mention. So if you read this picture again, one thing I want you to notice here is like here, actually, Alice and Bob, they always disagree with each other. They have opposite tastes for the fast food restaurants. And in such case, if we pay them according to the number of agreements, it won't work. But here, even though the matrix actually reflects this kind of negatively correlated thing, and the determinant of the matrix is negative. But if we like multiple 2 things together, in expectation, they're actually positive. And even though if in another case, if they have actually very similar tastes with each other, and in such case, the determinant of the counting matrix being positive and the product is positive as well. Okay, so that is kind of one way gives you one intuition that why you need to have these 2 groups in, because you want the expectation being positive. And more technical reason you need this 2 group here because you want the expectation of the payment being the determinant square. So that's just the technical reason. Okay. Okay, so let's start to prove the first property here. Still intuitively, you can understand the proof like this. We're gonna show that the determinant mutual information between the Bob's report and the Alice report after Alice performs strategy SA, and equals the determinant mutual information between Alice report and Bob's report times the amount of information contained in the strategy SA, and we just call it informativeness of SA. And sorry, in this case, we then gonna show that the informativeness of this strategy is always between 0 to 1, and then we have this inequality. And if you want to read the mathematical proof, here it is. So basically, it's just because with our previous assumptions, we make the joint distribution over SA, Alice, and Bob equals the joint distribution matrix over Alice and Bob times Alice strategy. And then because of like a determinant have this good multiplicative property, you can like detach this SA thing outside. And then the determinant of the strategy is just a transition matrix is always between -1 to +1, and its absolute value is between 0 to 1. So this determinant can be interpreted as the amount of information contained in SA, and then you finish the proof. Okay, so the next step is we want to show the expected payment of this DMI mechanism equals the square of the determinant mutual information between Alice feedback and Bob's feedback. As I mentioned before, that's the main technical reason we need two groups of tasks here. And one key thing we can prove is that for each counting matrix, its expectation kind of proportional to the determinant of the joint distribution over Alice and Bob's reports. And this is actually not that trivial as you think, because you may think like if you just like write down the formula, you can get it. But actually, the entries of the counting matrix are not independent of each other. So you still need to be careful here. But anyhow, this claim is still valid. And then once we show this, for each counting matrix, its determinant is proportional to the determinant of the joint distribution, which is actually the DMI, but without the absolute value. And once we show this, when you multiply the determinants of the two counting matrix together, you're gonna get something that is proportional to the DMI square. And still, I get another question when I gave this talk before is like, if you want this kind of thing, why you just calculate the determinant and square it? Why you need to divide the task into two groups and multiply them together? So that is because the expected of x squared doesn't equal to the expected the x expectation square. So ex squared doesn't equal to ex squared. And but if x and y is independent, we can use that exy equals ax times ey. So that is why we need two groups of tasks here. Okay. And the reason the two groups are independent is the assumption we made before. Remember, we assume that their reports are IED. So across the tasks, actually independent. The randomness is actually independent. Okay, so finally, we can talk about the scoring rule we get. So the scoring rule is actually just the mechanism, the payment of the mechanism. So if we have two participants, there is no way we can distinguish who is better than who without verification. But if there are three participants here, and actually we can, doing this thing, we can score each participant by the DMI square between, for example, Alice and Bob, and the DMI square between Alice and Charlie. And in such case, we can use this score to kind of like represent the quality of the participants' feedback. And we only need at least 3 participants here. And the reason this is a good scoring rule just because that it is actually robust in the sense that if there is a ground truth G, so we talk about different setting with a ground truth, like this non-subjective setting, if there is a ground truth G such that Alice, Bob, and Charlie's reports independent conditioning on G, and in this case, the score of Alice and score of Bob actually can represent their true DMI between their report and the ground truth, although we don't have access to ground truth. So it's kind of can identify your quality without ground truth. And this reason is just because, remember, the multiplicative property of determinant, we can actually put the informativeness thing outside the formula. And that one can give you this relatively invariance property. So I think I won't go into detail here. And the good thing about this theorem is that you can actually apply the theorem in the noisy learning case, because if we want to evaluate which classifier is better, and in this case, we can think Alice as classifier A, Bob as classifier B, and Charlie of the noisy labels, and the ground truth as the clean labels. And in this case, we can see because of the above formula here, even though we want to know the true distance between the classifier to the clean labels, but we don't have the clean labels, we can still use the trick of DMI to kind of relatively know who is closer to the clean labels with only the noisy labels. And from a theoretical view, the amount of noise actually doesn't matter here, as long as it is like, the noisy label is actually not uninformative. So that is actually a very interesting thing, and why it can be applied in this machine learning case. And this work has been accepted by NeurIPS. Okay. So finally, let's talk about the conclusion and future work. The main points of this work, it proposes a novel reward system that is dominantly truthful, prior independent, and practical. So I believe it can have some, it can be applied in practice in the future. And the one future work is basically we need to perform some real world experiments to show that it actually can be useful in practice. And another one is like maybe full characterization of all strategy proof mechanisms. And third one is the IED assumption. Like some people complain about this assumption, and maybe we can relax this assumption with a different setting, but still use the same information theory idea. And the last one is, can we do better than 2C? So one thing is like, I already showed that we can actually get a fattening of strategy proof mechanism with only 2C, with only a finite number of tasks. And but I think none of the mechanism I get has a better bound than 2C. And one thing curious is like, is 2C the lower bound? Okay. Thanks for listening. Any questions?
Thanks for the very nice presentation. So yeah, Yuqing, there are some questions from the audience. The first question is there a DMI for continuous or random variables?
Yeah, I actually think about this question before. I think one idea is like maybe extend this determinant thing to our continuous setting using some functional analysis knowledge. So maybe we can use some knowledge from physics, like the path integral thing. That's one of my idea, but I don't know whether it is very important to think about this question, because in some situation you can always discretize the signals, even in the continuous setting.
Yeah. The second question is, why does the strategy take the private signal of task T as input, but doesn't include the private signals of other tasks, given that the payment depends on all reported signals?
That's a very good question. Yeah, that's actually one restriction of this mechanism. It only takes it's kind of like the different definition of strategy from the one you're actually familiar in the general game. But the thing is, like, there is impossibility result, saying that if you take all the tasks, the private signals as input, you cannot achieve this good property. Yeah.
Yeah. The next question is your DMI mechanism is the only mechanism that is dominantly truthful under your assumptions?
It's not only dominant one, as I mentioned in the previous work. Case, yeah. So see, there is already 3 previous one, including one I designed by myself, by my previous collaborator and me. And the problem is they are strategy proof, but they are need infinite number of questions. And the one is the only one for now that can be dominantly truthful with only finite number of questions.
Okay. Yeah, thank you again for your very nice presentation. Yeah.